Okay, good morning, everybody. Maybe some more people will come in a little bit later, but I think we should start not too late after 11 o'clock for our next DASH webinar. Today, I'd like to welcome you to DASH webinar on the topic of AI in predictive infection management. And we will have Christian Luz and Dimitrios Soudis presenting today. I first will give a short introduction on DASH, and after that we will have the two presentations. So DASH is the Data Science Center in Health of the UMCG. As a lot of you will already know, we work as a team within the UMCG, not connected specifically to a department, but we are supporting all of the UMCG, and we have different areas that we are working on. We are running data science projects that we support. The call for new projects will be out shortly. We work on community building, and webinars like this is one of the things that we do to build that community of data scientists within the UMCG. Look at collaborations as an incubator, so look at companies to connect them to the UMCG based on data science project. We look at and help in obtaining funding. We can help you with writing data science work packages, for example, in projects, and sometimes we also actively participate in projects. We have a machine learning lab, which I am running. We look at the needs assessment, so we look at what is needed within the UMCG and what do we want to do with data science. What are the questions that are coming up when you want to use AI, for example, in clinical practice? We look at education on a broad scale. Again, this is one of the things that also falls under the education part. We also have short videos where topics are explained. They are also available on our YouTube channel. And we work on communication of what we do within the UMCG on data science, within the UMCG to let everybody know what other people are doing, but also outside of the UMCG with the University of Groningen, but also in the region nationally and internationally. So that's for the introduction of DASH. For the session of today, I would like to ask you all, if you don't have it already, to put your microphone on mute so we don't have any disturbance of background noise. If you want to ask a question to one of the presenters, then please raise your hand and wait for your turn. You can find the raise your hand button in the bottom of your screen. Alternatively, you can also type in a question in the chat, and then we will pick it up later. Because of the topic of today and the integrated presentations, we will do both presentations and then do all the questions in the end after the second presentation. So as I already said, Christian and Dimitrios are with us today to do their presentations. First, we will start with Christian. He is a PhD candidate at the Department of Medical Microbiology and Infection Prevention in collaboration with the Department of Critical Care. He has a background in medicine and global health, and in his research he focuses on clinical decision making and antimicrobial stewardship. Essential parts of his work are the use of routine healthcare data, data visualization, antimicrobial resistance reporting, machine learning, and the use of open source software. So with this, I would like to give the floor to Christian to give his presentation. Christian, can you?
Yes, thank you very much. And sharing my presentation now here. All right. Yeah, thank you very much for the introduction and the opportunity to present our research and our work on predictive infection management here at this DASH webinar. Here we go. Yeah, just already introduced by Peter. Thank you. Yeah, I'm located the Department of Medical Microbiology and Infection Prevention. Last year, PhD student there, and in close collaboration with the Department of Critical Care. And I have supervisors on both sides. And my research project is part of a larger PhD project called the Pancreas Project, and also part of the Microbes in Health and Diseases program. And today's work or presentation, and in this project is in collaboration with the Data Federation Hub, the data science team at the CIT. And we were very lucky to have been awarded a grant working with them during the or from the call in the call Data Science in 2018. And since then, it has been really a fantastic project and collaboration. And what we're showing today, me doing the first part, and then Dimitrios taking over for the Data Federation Hub side in the second half, is the outcome of this, which started 2 years ago. Yeah, so my background is I'm an MD, and I fell in love with data and working with data, and especially with routine healthcare data, predominantly coming from hospitals, so electronic health or electronic medical records. I'm not based in the lab, just sitting in front of my computer and doing these times at home, obviously, as many or probably most of you also right now. And I'm actually calling in today from Cologne in Germany. So my background, or kind of what I'm focusing at, and Peter already mentioned that, is antimicrobial resistance and antimicrobial stewardship. The latter is just a set of concepts that tries to prevent this precious resource of antimicrobials or antibiotics also for the years to come. And trying to tackle and find new ways to tackle antimicrobial resistance. And my work has been centered a lot around, also on the one hand, really trying kind of to find new ways in working with antimicrobial resistance data. And we're doing this predominantly in R, so using open source software for this. And we've developed packages to do this here on the left side, the AIM-R package, helping us achieving those goals. But also trying to develop new ways of interacting then with the clinical side through dashboards and data visualization tools to create better feedback loops. And then all that, of course, like is centered or somewhat integrated in infection management. I want to just briefly talk a little bit through it, what we mean by that, which is also important, of course, for this research project that we're presenting today. So in a very simplified manner or form, we have this kind of flow where a patient comes in with a suspected infection. We are then testing, of course, with diagnostics or microbiological diagnostics, getting a diagnosis, treating the patient if it's a bacterial infection with antibiotics, and hopefully the patient leaves in a better state in the end with an improved outcome, healthy. The tricky thing with infections, but also the interesting part, I think, is that we're in this phase where at the beginning we're suspecting infection, but we don't know the underlying pathogen yet. And diagnostics for that can take up to 24 or 48 hours. Sometimes even longer, but we already need to initiate typically treatment at the beginning. So we have this period and phase where we actually do not know what the underlying pathogen is, and we can just adjust our treatment and really refine it when we have a positive outcome of the diagnostics, or when the diagnostics show us what the underlying treatment is, and then we can go back and adjusting the treatment exactly to the pathogen or the bacteria, for example, that was isolated in the diagnostics. And before that, so this is what we're calling empiric therapy, because it is of course not entirely in the blind, but we're basing the treatment choice on patient characteristics and but predominantly also, of course, on the local epidemiology. What we know is, for example, circulating in the area or in the region or even in the hospital. So we can adjust our treatment, but we cannot narrow it down before we get the results of the diagnostics. So essentially, we have, but we still have this blind spot at least a time where we do not have enough information at hand yet, and kind of an incremental knowledge gain over time. And now there are several ways to address this. One is, of course, the typical way is retrospective, and this is kind of where the first two research project examples I showed you come in, where we go back, look at surveillance data, the epidemiology, feeding back this information so to make better decisions based on what we know is happening already. But it's very retrospective and very reactive. And it would, of course, be very nice if we can also go on the proactive side, on prospective or predictive infection management. And for this aim or goal, and also what this research project is about that we're presenting today, we looked a little bit what has been done so far in the past. We did this review, it's a narrative, it's not a systematic review, on machine learning and infection management using, that's important, routine electronic health records. So no study data, really just data that is already there and available in hospitals typically. And what we found is we looked at 52 studies that were very scattered, like all over different aspects of infection management. Here ranked from the top, the most frequent one down, and sepsis is definitely a very prevalent topic in the field. Many studies trying to tackle this, like 19 looked at sepsis alone, hospital-acquired infections, surgical site infections, etc. So many different angles to infection management and different outcomes, but we also found very, very heterogeneous approaches, so ranging greatly in study size, how many patients were included, how many features or variables were included in the final model, but also 35 different machine learning techniques and range of best model performances. Overall, we found a very nice examples of LSTM, long short-term memory neural networks and artificial neural networks, but also logistic regression models performing really well. However, of course, it is basically not really possible kind of to really compare all those different takes and approaches to infection management, because the outcome is so different and the approaches is so different. And unfortunately, we also found that in this very young field in infection management, at least the reporting standards are quite low, so it's often difficult to compare. But nevertheless, it was very informative for us, and the places just mapped it here now, kind of where the different studies in the past also try to look at, were really on, for example, the diagnostics, predicting sepsis, or trying to make a diagnosis, but also trying to predict the outcome of diagnostics, trying to predict or model the optimal treatment in this blind spot phase, but also a lot patient outcome in the end. Mortality, of course, is a big one here. But what we're trying to do now, and now coming kind of to our take and our project, and the topic of today is the management aspects in here. So something that we didn't see here yet kind of is, we all, of course, also like this very hardcore or hard-coded diagnostics, yes and no, and sepsis, yes and no. Also, that is difficult to derive sometimes, but also mortality, yes and no. And what are the management aspects here, and what is actually infection management, maybe at a little larger scale? Also adding to this is something that's interesting to see. Of course, we know that electronic health records Well, they're not meant for research in the first place. They're meant really for the patient care as a primary goal. But of course, we use this a lot, and it is also, and it's shown that it's great and can be leveraged for research and also for other takes. But this study here, for example, also assessed a little bit the biases in electronic health records. That is often dirty and messy data. And they found that just the sheer presence of a lab test order has significant association with the odds of survival. And they also found that the data about the timing of when a lab test was ordered was more accurate than the test result in predicting survival. So we also see that kind of there's another layer or level to electronic health records, and that kind of management aspects are kind of within this data also, which is, for example, just the taking of a test or when a test was ordered, etc. And that's also very important information. And one important aspect in infection management is also that it is never really done alone. So what is typically the case is that infections are managed in a multidisciplinary way. So, for example, there might be a patient on intensive care unit with a infection, and additional experts from outside the intensive care unit come in and also consult the intensivists on this patient case. So, and that is in our scenario now done with microbiological consultation. So a microbiologist coming in, being part of the team and advising the optimal treatment and diagnostics aspect within this patient case. Microbiological consultations can be triggered through various ways. Of course, intensivists can call a microbiologist, ask for advice. A diagnostic test can trigger a consultation. Treatment, even in some settings, automatically can trigger consultations, or just the patient characteristics can also be a trigger. And all this forming these microbiological consultations, and this is what we're looking at now, taking this as an indicator of our management and our multidisciplinary management. So who are those patients, and which patients might need a microbiological consultation as an indicator of this management aspects. So our take here is now really like, predicting microbiological consultations at the intensive care unit. So to model this multidisciplinary approach, it's kind of a proof of principle. As I said, it's kind of new, it's a little different from what's been done previously in the past, but we still see a great potential, and it could eventually improve the management, but also the workflow, also creating new triggers. It's helping with diagnostic stewardship. That means getting the right test at the right time to the right patient. And the same applies to antimicrobial stewardship. Those two are very integrated and closely linked, which is basically just getting the right antibiotics to the right patient at the right time, and then eventually improving the quality of care for the patients. So the setting where we're doing this or carry this out is based at the UMCG, at the intensive care unit. The patients we included come from a phase where the MetaVision database was in place, and that is the electronic health records system or database in place before EPIC, and it ran from March 2014, where it was phased in and then stopped with a switch to EPIC in December 2017. So all patients in this database were available to us and included in the study, and we looked at patients over the age of 18 years. And it was, of course, approved as non-VMO by the METC, and we checked for patients not being in the UMCG objection registry. We added a couple of other databases, coming to that in a second, from the UMCG, but also from LIMS, which is located at the Department of Medical Microbiology. just a quick overview now how many patients we included. We had a little over 9,600 admissions from 8,270 patients, unique patients. So we had a couple patients that were admitted more than once or readmitted. The proportion of patients receiving a microbiological consultation was stable over time with no significant changes here, centered around like 8.55%. So the data bases, I already mentioned MetaVision. So what we got in this database is a little under 2,000 raw parameters that comprise lab results of any type, point of care tests, vital signs, of course, line placement, so indicating, for example, the presence of an IV line, what kind of line, but also prescriptions, for example, about antibiotics, but also all other kind of prescriptions, really everything. We added to this data coming from the UMCG, demographic data, but also administrative data, for example, whether an admission was kind of a planned admission or more kind of type emergency admission with an admission to the ICU was done through or via the operation room, for example. And then very important, of course, this GLIMS database, which is located at the Department of Medical Microbiology, where we had information about all sorts of microbiological tests. We did not use the outcome of the tests, but just whether a test was ordered. And then very important, of course, the consultation, where this is our target prime outcome here, or target, in the first timestamp. And what I mean by that, also coming to this in the next slides. So the pre-processing of the data, what we did is we tried to just include variables or features that were present in at least 30% of all patients, and that already narrowed it down to 121 parameters. We went ahead and, of course, like did intensive checks and cleaning the data, also with a clinical focus, seeing that non-physiologically possible data points were removed or cleaned from the data, which is often an issue with electronic health records. We also introduced new features based on the reference range, for example, for lab parameters, to see whether parameters fall within this range or not. And we had data on very, very high resolution. We also on a minute level, and we aggregated kind of to have one data point, which could then sometimes be the mean aggregate, for example, on a minute level, and moved on from there. We also introduced a couple of binary variables per time point then, and for example, indicating the presence or absence of line placement. We did the same with prescriptions. So we did not look at the dosing, for example, but just whether for example, antibiotic treatment was present or absent at a certain time point. And then our target and outcome was then consultations. So within the GLIMS database, we have available information when a consultation was registered in the system. And we took the first timestamp. There could be more than one consultation. The first timestamp is our target. We also, in theory, have notes available. What we did not look at those notes in this study here. We also had no information on the type of consultation, so whether this was in person or by phone, for example. So in the end, this parameter or this variable indicated whether a patient, or kind of when a patient first appeared on the radar, really, of a microbiologist. And with that, just thanking our team here, and now leading over to Dimitrios, who is going to continue on more data science aspects and the modeling parts. and looking forward to your questions later on.
Okay, thank you, Christian. We move on to Dimitrios, who is a data scientist at the Center for Information Technology of the University of Groningen. And he supports projects in genomics, medicine, computational journalism, chemistry, and consultancy, so all kinds of different fields. And one of the projects that he was involved in is the one of Christian, so that's why he is here to share his experience with that. So, Dimitrios, on to you.
Okay, thank you, Peter. So, hi everyone. So the introduction was done. I'm a data scientist. I work for the Center of Information Technology, and we are part of RWTH, not a part of the UMCG. And so today I'm just gonna start a little bit with talking about our team very shortly. Some of you may not know about us. I'm going to talk about PRIME here. Is the that's the abbreviation of the project. So primary predictive infection management, and from our side at least, the data science team side. And then I'm going to discuss a bit about the stages of the projects, so how the data came and how we wrangled with it. And I'm going to go into a little bit more details. So Christian gave you sort of the overview. I'm going to discuss a little bit more the nitty-gritty stuff. And then I'm going to go into the modeling phase. And there were two modeling phases, the first one and then the second one. Future directions, yeah, okay, it's very small, and after all, it's not sort of okay, the message was not for me. So future directions is not so much our job, right? So we're here to support the researchers, so I'm just gonna briefly mention them. So just to start, so I'm part of this team data scientists, team data science. We are part of the Center for Information Technology for the University of Groningen, and we work with researchers and we try to sort of enable them to use machine learning or statistical techniques in their research. You don't have to really know how to use these techniques, so that's where we really thrive. But even if you know these techniques, we can still support you, and maybe you know something we don't, and we know something that you don't. And we have a call for proposals, one per year. So 2 years ago, Christian was one of the awarded investigators, and there are more on this in our website. So instead of giving you here a very long link that you won't even get access to, if you just Google, CIT, RWTH, and data science, you can come to our webpage and you can see more about our projects and what we do and when you can apply for the next time. So. Okay, so from our side, okay, this was a challenging project because it had several layers of complexity. So first of all, we had to wait until some legal and ethical issues are solved until we get the data. There were different stakeholders there, and so it was us from the CIT. It was the intensivists from UMCG, it was the medical microbiologist teams, and so all of this had to be nicely coordinated. Of course, everyone was really willing to do that. There were no hiccups or anything, but it was something that sort of taught us that many times it is not just getting the data and doing your job. There's so many things that you have to solve before you can actually dive into the data. And then when the data came, that's, at least for me, and I think for the rest of the people in my team, the fun part. So it was kind of challenging, but that's part of the fun. So there was a lot of things before we could actually get the data, our hands on the data. So we had to anonymize the data. We didn't do much of that. Christian was excellent and his team to do that. And we had to build a little bit of infrastructure to share the data, because as you know, you cannot just put that kind of data into a USB and just say, go ahead, use them. And of course, we had to do all this onboarding between us and the doctors and the microbiologists. We had to explore some hypotheses and share some interdisciplinary knowledge, because we did not have experience with that. And again, it was mostly Christian's contribution here, going through the literature, finding out what similar things have been done, and giving us sort of the direction that we needed from a theory point of view, right? Because we have no idea about, well, we had no idea about analyzing data like that. And so when we actually got to the point where we got the data, we received basically 11 files, right? So there were information about the patient's vital signs, the kind of medication they were on. In the beginning, there were comorbidities. I don't think at this point we have used them yet. So there were like these lines, and for people who are not familiar, these lines are basically IVs, catheters, so stuff that you can sort of hook, I guess, to a patient. And so they are important because they can be carrying germs every now and then. There were some lab tests, so whether a certain bacteria was present and so on, cultures. And there were, you know, at some point we were working with 1,500 variables, and they were all down to the 1 minute interval. And in the first sort of attempt, I tried to combine everything together, but I ended up with a database with 55 million rows and 1,500 variables, very sparse. Of course, it's very exciting to be able to do that, because this means you only have choices. You can start slicing and dicing and end up with something nice, which is what we did. And so just looking at sort of the sparseness of the data, we all thought, okay, so keeping the data at the 1 minute interval, maybe it's a little bit too much. So we started thinking of ways to aggregate them. So we went up to 1 hour, 4 hours, 8 hours intervals, right? So we take, for example, imagine the vital signs of a patient within, they were observed for every minute, but then instead of doing that, we could have their average or their median for every 1, 4, or 8 hours. So the final resolution chosen was the 8 hours because it kind of made sense. So I think I have activated the pointer. Yes, you can see it now. So for example, if a patient spent the whole of Monday inside the ICU, we would end up with 3 data points for this patient. So it would be midnight to 8 o'clock in the morning, well, a little bit before, 8 o'clock until almost 4, and then from 4 until 11:59. And this kind of made sense. I heard the noise somewhere. I don't know if it was me or someone else. So this kind of made sense also conceptually, right? Because people work more or less close to these hours. So it was a little bit like looking at different shifts. So kind of aggregating the information from a shift. So some, let's say, intensivists that spend the night there could sort of inform the intensivist that comes in the morning. So this was the aggregation phase. And before that, of course, we had to deal with a lot of missing values. What we did here, we followed the literature that Christian shared with us. So for example, we moved forward the last known measurements, so to a little bit go back and help you visualize that. So if we had an observation about, say, the blood pressure of a patient for 12 to 8 in the morning, but somehow we didn't get a data point for the next shift, we just moved forward the next one. And of course, we don't do these things just out of our head. So first of all, we saw that this is done in the literature, and then talking to Christian, he said that kind of simulates what doctors do, right? So if you don't have any new information, you're going to use the last available, and moving forward, point in time is basically that. And then if there were any more missing values well, if there were any more values missing, then we just imputed using the median. But at that point, the data set was almost, let's say, 93% complete. So there was very few missing values, and imputing them wouldn't cause much of problems. A few anomalies and outliers that Christian mentioned. So what we did is then again discuss this, and we saw that something is not, let's say, physiologically possible. So just for an example, so if you saw someone with a heart rate of, I don't know, 600 per minute or something, that's not possible. This must be a measurement error. So what we did with these observations is we sort of clipped them. We brought them back into the distribution that we observed in the data, right? So let's say we clipped it into 4 standard deviations away from the mean for that variable. And another thing we did is that patients that were admitted multiple times, they were treated as independent observations. So if I spent some time in the ICU on March, and then I ended up again there in, I don't know, April or May, some other month, we saw that as a different admission, right? And as a, let's say, an independent event. But of course, we kept a variable that signified that this is a readmission. And finally, we dropped a lot of variables that didn't contain significant variation. So just as an example, there was this one variable that indicated whether a test was done for a certain bacteria, Pseudomonas, and that just happened, let's say, 2 times in the last 5 years. So you could imagine this as a variable being basically just zeros and just somewhere a unit and then another unit. So these kind of variables can cause models to overfit. So we started dropping them, at least in the initial phase, and we would have used them again if we didn't get the results we were looking for, but things turned out great. So far they're just back there in reserve, haven't used them yet. So just doing all of these choices left us with 60,000 observations. They represented more than 13,000 unique admissions. Okay, just remember though that readmissions are treated as independent observations. And then initially 55 variables. As you will see later, we dived in and brought some more variables. So we tried to predict, sorry about this, it was just a distortion from turning this internally into a PDF. So we tried to predict consultation 8 hours in advance, right? So imagine again, a patient spends all of Monday inside the ICU, and we have data up until Monday, 1 minute before 12 o'clock. Then we try to predict whether this patient will need consultation, or whether, let's say, a doctor would make a call to the microbiologist help desk by Tuesday, 12 o'clock, which is sort of, let's say, the next shift. So that was the idea behind modeling. And then let me tell you a little bit about the first phase of the modeling. So when we started with a model called, let's say, at the door. So when a patient is admitted in the ICU, we already know a few stuff. We know about their gender, their age, the BMI, whether they were on mechanical ventilation, right? So whether their breathing was supported. We know which specialty sent them. We know whether it was a planned admission or not. The type of admission, was it emergency, medical, or planned surgery? Whether it was a readmission, and a variable called VIK, which, if I recall correctly, means whether this patient came straight from the surgery or not. So it was kind of tempting to think, okay, before going into anything about what's happening in the ICU, can we sort of use, see how predictive these variables are already? So that's why this model is called at the door, because this is basically all you know about a patient as soon as he or she shows up. So can we already predict something? Here we tried, so these are the best models that came out. We tried a random forest model and a gradient boosting machine model, and their AUCs were around 0.75. So okay, not the best thing you can do, but then again, not hopeless either. And we looked at sort of the variable importances for the two different models, and you can see they were kind of agreeing. So the number one factor was whether it was a planned admission or not. This really helped the models learn. Whether it was a readmission, the age, the rest received much less importance. So this was kind of a nice experiment. Of course, this is not where it ended. So we wanted to know, it was a way to sort of also figure out how much the things that happen in the ICU affect the outcome or not. And of course they do, right? So in the next approach, we're still in phase number 1. We started collapsing the time series. So we took the averages and the standard deviations of all the 55 variables for up to 48 hours before, let's say, the point that we wanted to predict. And we tried to predict the next 8 hours. So here's sort of a sketch. So we would take all of the points from Sunday and Monday, compute their averages and standard deviations for all these 55 variables, and then push them into the same models and try to predict Thursday in the morning. And the way this worked was, of course, better because we now have information. We have 55, so we increased our features by a huge number. And of course, the AUCs were much better now. So again, not the perfect, but we were closer to 0.85 at this point. And looking at sort of the importance of the variables used, you can see that a lot of them was about what's happening in the ICU. So this is fake algemeen, for people who don't speak Dutch, like I didn't, is sort of taking a culture, a general culture, ordering a test, and a culture here, just in case people don't know about that, is basically when doctors take a sample and then they cultivate it and see what kind of bugs show up. And it was also about more specific cultures later on, whether antimicrobial medicine was given to the patient, whether it was a plant admission. Again, this still kept showing up. And basically, it's a lot about cultures up here. And here start the vitals of the patient. And then again, sort of a mixture of vitals and vital signs and cultures. So these are sort of, I think, the top 20 or something informative features. So this was going well, okay, fine. But instead of sort of taking averages and so on, could we do something better? So we thought about, okay, what we've done so far is sort of take averages over 48 hours, right, and try to predict. Instead of that, why don't we use something that can actually use the time series as is, right? So let's turn into recurrent models. And an alternative that is, it was very popular also in the literature that Christian shared with us, was the long short-term memory neural network. So this is a model that doesn't need us to calculate average and so on. It does what we call automatic feature extraction. And of course, at this point, the results were quite similar to the other collapse time series. There was a slight improvement, maybe not so statistically significant, but the gain here is that we did no pre-processing. So if you imagine these models being used, let's say, in real time somewhere in the ICU, we don't need a step in the pipeline where we average stuff and take their standard deviations. We can just feed the raw time series into this model, the LSTM, and get the same kind of output. So even though it doesn't sound like a much improvement, I think it reduces the burden of applying this type of modeling in real time, right? And this is kind of a summary of what happened. So we see that what really matters, what makes it a big difference is what happens in the ICU. And we see that, okay, it's not so much about what kind of algorithms you use. It's, looking at the numbers, they seem pretty comparable. So it's not so much about what kind of algorithm you're going to use. It's about what you're going to feed your algorithm with, what kind of information. And of course, I mean, everyone knows that this is the case always. So that's when Christian went back to the lab, but not really the lab, because he told you he's not lab-based. He went back into the databases that they have, and he came back with more features. And we started cleaning these variables, aggregating them, and going into phase number 2, where we went from 55 variables to 120. So we got more vital signs, and I think also the way that we coded for some tests and some medicines that are given to the patients was different. So we tried to feed our algorithm with more and more information. We went straight to LSTM because we knew that it works as well as other algorithms, and it saves us a whole step of pre-processing. And the results just jumped to an AUC of 0.93 when we went up to 120 variables. So this was very nice, and yeah, that's basically a summary of what we did. And of course, there were a little bit more experimentation, but this is sort of what came out in the end and what worked. And I think for sort of future directions, maybe we could look at how to sort of simulate a real-time use of the trained models, maybe try to estimate potential benefits, like Christian said. So if going into beyond a proof of concept and going into the ICU and trying to use a system like this, what are the gains here? For example, you will skip some unnecessary testing. Maybe you will have faster interventions. So exciting questions to go and look for in the next round of this project. And that basically concludes everything I had to say for this. And we'll need to leave some time for your questions. So I guess I will just stop sharing now, or yeah, so we can start the discussion and start hearing your questions. So thanks for listening.
Okay, thank you, Dimitrios. Very nice presentation. Is there a question from somebody from the audience? I don't see anything in the chat yet. We have a question by Alessia. What do you do to avoid overfitting when adding so many variables in your LSTM?
Yes, well, that's a good question. So the way we worked with that is, so first of all, before starting and let's say feeding these variables into an algorithm, first of all, we checked a little bit about their correlations and so on, and we looked at, they were not so overly correlated, so they all captured sort of different information, and so that tells us that we at least don't seem to have many redundant variables. So another thing that we did was from the beginning to make sure that these variables contain enough information, enough variation. So like I said, we kicked out a lot of variables that had very few meaningful observations. So imagine a variable, so we had like 30,000 observations. Imagine a variable that has 25,000 zeros and then just 5,000 ones. Maybe this is informative, maybe not. So we took this approach. We said the kind of variables that we're going to include must have enough sort of variation. So this, I think, was the main step that we took to predict overfitting, right? And then beyond that, what we did is we used a part for, so while the LSTM was training, we used a part for, let's say, cross-validation, of course, and then we had some cross-validation results, and we compared them against a final untouched test set. And when we saw that those two were agreeing, we knew that there's very little chance that we're overfitting. So to sort of summarize, we made sure that there are no redundant variables. The variables included were they had enough variation, and we used let's say three-way split of the data set, so one to train and another one for a final test. Well, one to train, one to cross-validate, and one for a final test.
And could you also do a validation in a independent data set, or you use?
So far, I think we used everything we had so far, and maybe later on we can get our hands to a completely independent, let's say a publicly available or something like that data set. But the problem would be that, well, I don't know if it's a problem, but so we had so much information that I don't know if it will be possible to get another data set with the same type of information.
Okay, there's also a question from Hoon through the chat. Also for Dimitrios, I assume that you use sequence lengths of 48 hours, like for the collapse time series model. Is this right? If so, did you also use different sequence lengths for the LSTM?
Okay, so for the LSTM, we did not. I did a little bit of let's say in the end. So the sequence I used was 10. So it wasn't a sequence of 6. It was of 10. So we're talking about 3 days plus, point something instead of 2 days length. I also tried with 4 and with 6 and a little bit more, and it seemed that sort of the cross-validation and later the test results were better with a 10 sequence length. The reason why I used that was because I sort of looked at the distribution. So what's the average length of the what's the average stay in the ICU? And let's say there was a median of 4 point something, so let's say 5. And then if you look at the empirical distribution, about 80% of the patients stayed in the ICU for less than 10. So by using a sequence of 10, I was capturing, I would say, most of the information. And then, yeah, that's how it ended up with being 10. The sequence was 10. The sequence length was 10.
Okay, thank you. Hung says it's clear. Thank you. Maybe also a question more for Christian. We hear from Dimitrios that he used his models, and then there was a couple of features that were the best predictors that scored very high. Were these also the ones that you would expect, or did you see any surprises there?
Yeah, absolutely. No, that was of course also important for us. I mean, also like validating a little bit was what came out there. So most of the predictors that came out, for example, also from the at the door model, that were really fitting our expectations or matching our expectations. So the ICU patient population is somewhat special because I mean the population also is very heterogeneous, and we saw this variable popping up, planned admissions, that, for example, often our patients come, for example, undergoing heart surgery, going to the ICU to being monitored very closely, but don't stay very long, maybe 24 or 48 hours, and then leave. And those patients typically, like, we do not expect some infectious complications or microbiological relevant complications to show up. So that matched, and there were no real surprises in what we saw in the feature importance actually, but more validating.
Yeah, so that also helps in the acceptance of the ICU doctors of such kinds of algorithms, that they can see that it's not doing something that they don't understand, but it's something that they can also reason by themselves, that would be logical to use those specific features to make those decisions. But that's an interesting finding. I think also maybe Dimitris can confirm, but I think it's interesting that you also showed a lot of the discussion that we get, and a lot of the questions that we also get there, so that everybody starts to ask, how many patients do I have to add into my database? And to improve it, adding more patients and more patients. But now you also showed that it's might not be just adding more patients, but also more variables in there, or more features, could also improve your prediction.
Yeah, so from my part, I think that's the most important piece that you need to add, because so people sometimes say, okay, big data, but they just mean that I have a lot of rows. But okay, fine, that can be useful, of course, because there's something called the curse of dimensionality. So if you want to if you have this lots of variables, lots of features, and you want a model to sort of pick up interactions and nonlinearities, yes, you need a lot of rows. But the truth is, if you think about it, what if you sort of created a variable that captures this nonlinearity and added? So think about a simple linear regression with a simple term and then a squared term. Okay, so if you have a lot of rows and you use a complicated model, it will capture the squared. But if you just know that this is what I need, you give it to OLS, you will end up in the same region. So for me, it's kind of like the information that you feed to the classifier or whatever. It's extremely important.
Okay, thank you. Any other questions from the audience? I don't see anything in the chat anymore, I think, and I also don't see any hands raised. So if there are no questions anymore, then I think we can wrap up for today. Christian and Dimitrios, again, thank you very much for your presentations. I think it was very interesting to see this application, to see the way the collaboration can be set up between the data science group of the CIT and the UMCG. I think we should see that more often in projects. So thank you very much for also showing that collaboration here. And for everybody that is listening and that will look at this later on, keep an eye open for the calls that the CIT puts out for data science support, and submit your projects if you want to have some extra support to try and get something more out of your data than just looking at it and doing the regular statistics on it. So thanks again, and yes, this is some extra information about DASH. If you want to get more information, you can go to our webpage or send us an email. Also look at the LinkedIn Through the webpage, you will also get to our YouTube channel where you can see these recorded sessions of the webinars and also our mini classes that we have on there. So thank you all for being here. Until next time.